So I hope y'all had a good weekend. Some of you I saw yesterday in the T lesson, but either way, welcome back. Today we're going to be getting into section 11.2, which is the second part of chapter 11. It will build off of what we learned about chi-square tests in section 11.1. A couple of things before we jump into that. All the resources should be ready to go in Canvas for chapter 11. So I've got both study guides available for section 11.1 and 11.2. All the practice problems and solutions for both of those sections are posted as well. So everything for chapter 11 within that last module, the last unit module, are ready. So please be aware of that. This may give you some resources that you can study with. So there's that. Also, I have updated grades again. I kind of do that every Monday. So it's your grade in Synergy should reflect the grade you have in Canvas, save for maybe one or two people who have submitted things since I updated the grade book, which there's a couple of people that submitted stuff after I updated. So that may not reflect, but you should check Canvas for the most accurate grade. And again, this grade update included placeholder grades for chapter 10 assessments. So if you have not done the multiple choice assessment, and if you have not done the free response question, then you have placeholder grades for those until they're submitted, to show you what your grade will be if they're not done. Because, you know, we're getting down to the nitty gritty of it, so I want you to have as much information as possible. So there's that. And then again, we'll have one more pair of assessments, multiple choice and free response, for this last unit. Yeah, I'm going through chapters 12 and 3 right now, trying to decide how to best kind of round that out and not spend too much time on it, because I do want to do some review before the exam and give you all some time to just get things done overall, if that is what you need to do. So there's that. Yeah, so there we go. So we're going to get started with our chapter 11, section 11.2, with a little PowerPoint presentation. So we'll get this rolling. Gotta share my screen. Yep. There we go. All right, so this is section 11.2, which is inference for two-way tables. All right, section 11.1 was dealing with inference on one-way tables. All right, still dealing with these distributions of categorical variables and categorical data. But now we're looking at two-way tables where we're comparing essentially two different categories of variables. All right, so that's the idea. So after this section, you should be able to compare conditional distributions for data in a two-way table, state appropriate hypotheses, and compute expected counts for a chi-square test based on data in a two-way table. You should be able to calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test based on data in a two-way table. You'll be able to perform a chi-square test for homogeneity and a chi-square test for independence, and choose the appropriate chi-square test. All right, something to note right here at the beginning, and I'll review this again at the end of the slides. The calculations that are done for these tests are identical. All right, whether you're doing a chi-square test for homogeneity or a chi-square test for independence, the way that you calculate the chi-square statistic, degrees of freedom, p-value, and all that stuff are identical. All right. The main thing is to know when you're doing a test for homogeneity and when you're doing a test for independence. What are the conditions that say we're doing one or the other? Because depending on the test, changes how you write your hypotheses. But the actual calculations remain the same. All right. So we have the two sample Z procedure from chapter 10 allows us to compare the proportions of successes in two populations or for two treatments. What if we want to compare more than two samples or groups? More generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? We need a new statistical test. The new test starts by presenting the data in a two-way table. Two-way tables have more general uses than comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. All right, so we'll start just by comparing distributions of categorical variables, though we will use this same set of data for our example later. Market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a Mediterranean restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the numbers of customers who ordered French, Italian, and other entrees. Okay, so essentially we have 3 different treatments. The type of music is the treatment. And so we have here the table of our observed data. We want to calculate the conditional distribution and proportions of the entree ordered for each treatment. So for example, with our treatment of no music, the distribution of entrees ordered was 0.357 French, 0.131 Italian, and 0.512 other. When we have the treatment of French accordion music, we have 0.52 French, 0.013 Italian, and 0.467 other. And lastly, our last treatment with Italian string music, we have 0.357 French, 0.226 Italian, and 0.417 other. And we can put these into bar graphs to make the comparison a little bit easier to compare those conditional distributions. And essentially, we want to look at this to come up with an idea. Is there a difference? Are the treatments causing something to happen? Because if we saw these being exactly the same for each treatment, there wouldn't really be any motivation to actually conduct the test. All right, but we do see some differences. All right, the type of entree that customers buy seems to differ considerably across the 3 music treatments. Orders of Italian entrees are very low when French music is playing, but are higher when Italian music or no music is playing. French entrees seem popular in this restaurant as they are ordered frequently under all music conditions, but notably more when French music is playing. For all 3 music treatments, the percent of other entrees ordered was similar. So we've done just a preliminary comparison using our two-way table and comparing the distributions. The problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions is common in statistics. This is a problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have 2 parts. Number 1, an overall test to see there is good evidence of any differences among the parameters that we want to compare. And number 2, a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. A follow-up analysis is only necessary if significance is found. Essentially, if you reject the null hypothesis, then you should do a follow-up analysis. The overall test uses the familiar chi-square statistic and distributions. So again, similar to what we had in section 11.1, we need to avoid the whole multiple comparisons. It's possible that we could do a bunch of 2-sample tests with this, z-tests, and compare the proportions and this and that, and have, multiple things, but we could find significance in one spot and not another spot, and that can cause problems in making an overall conclusion. So we have this other test. Right. Similarly to what we had to do in 11.1, we need to do expected counts. Right, a chi-square test for homogeneity begins with the hypotheses. The null hypothesis is that there is no difference in the distribution of a categorical variable for several populations or treatments. And the alternative is that there is a difference in the distribution of a categorical variable for several populations or treatments. We compare the observed counts in a two-way table with the counts we would expect if the null hypothesis were true. Sorry. Does anyone need a moment to write anything down about our hypotheses? All right, so consider the expected count of French entrees bought when no music was playing. Right, the expected number would be 34.22. Right, and this is found by taking total number of French entrees divided by the total, like the whole table total, times the amount of the sample size for no music playing, essentially, kind of. Right. Now, that explanation doesn't really help, so we'll get a little more here. The values of the calculation are the row total for French wine. I don't know why it says French wine. For French food. The column total for no music, and the table total. We can rewrite the original calculation as row total times column total divided by table total. 99 times 84 divided by 243, and that is 34.22. We use a similar approach for each entry on this table. Right, so we'll end up having 9 expected counts on this table. I can summarize that here. So when finding expected counts, and this is for a test of homogeneity or test of independence, we find the expected counts the same way. When the null hypothesis is true, the expected count in any cell of a two-way table is the row total times the column total divided by the table total. Then we have our conditions for performing a chi-square test for homogeneity. So whenever we perform inference, there are conditions to check. We have our random condition. The data come from a well-designed random sample or from a randomized experiment. There is a little piece missing from this definition for random, and it comes up later. When we're dealing with a test for homogeneity, there must be random samples from independent populations. So essentially, they're independent random samples. Or the treatments, essentially, right? Randomized treatments. We have a 10% condition and large counts condition that are the same as we've seen them for other chi-square tests. Right, we check the 10% when sampling without replacement, and that all expected counts are greater than or at least 5. Does anyone need a moment to write anything down from this screen? Just as we did with the chi-square goodness of fit test, we compare the observed counts with the expected counts using the statistic chi-squared equals the sum of observed minus expected squared divided by expected. This time the sum is over all cells, not including totals in the two-way table. So in this example, we will have 9 things to add together. And we got our tables again right here. For the French entrees with no music, the observed count is 30 orders and the expected count is 34.22. The contribution to the chi-square statistic for this cell is 30 minus 34.22 squared divided by 34.22, and we get 0.52. The chi-squared statistic is the sum of 9 such terms. Notice it is not showing all 9 parts. Just kind of summing it up here. So we have chi-squared equals the sum of the observed minus expected squared over expected, which is 30 minus 34.22 squared over 34.22, 39 minus 30.56 squared over 30.56, and so on. When you are showing how to do this type of calculation on the AP exam, for example, you do not need to show all 9 components. It's not necessary. If you show the first couple to show that you know what the calculation is, and then the last one, and then have your calculator do the work, which we'll see how to have your calculator do this tomorrow, then you can essentially just write what it is at the end. You don't need to show each component and what each component is equal to and all that stuff. Is there anything I can clarify about this step? So then earlier, we stated a significance test of the null hypothesis that there is no difference in the true distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Versus the alternative, that there is a difference in the true distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. I want to point out these statements are essentially identical except for they're saying there is no or there is a. Other than that, it's copy paste of the same thing. Right? There is no reason to write them differently. The only thing that has to change is that there is no difference or there is a difference. The no difference is always the null hypothesis. We have our observed stuff here, and then we already checked that the conditions are met, and our calculated test statistic is chi-squared equaling 18.28. So next we're going to use table C to find the p-value. Then it'll show the command and everything and how to use this on your calculator. Because the two-way table has 3 rows and 3 columns that contain the data from the study, we use a chi-square distribution with degrees of freedom equaling 3 minus 1 times 3 minus 1 equaling 4, right? Because 2 times 2 is 4, to find the p-value. And that is the number of rows minus 1 times the number of columns minus 1. So again, our degrees of freedom are based on essentially the number of categories. Has nothing to do with the sample size. We have our little section of table C here where we have degrees of freedom 4. Right, the value of chi-squared equaling 18.28 falls between the critical values 16.42 and 18.47. Corresponding p-value is between 0.0025 and 0.001. Sorry, that's typo. It is supposed to be 0.001. So sorry about that. In the calculator, you can use the command chi-squared CDF, and then in parentheses, you will enter the chi-squared statistic, an upper bound essentially, which is just a large number because our chi-square distributions is always just a greater than some value of chi-squared. So the value of chi-squared is a lower bound, upper bound is just a big number. And then the last entry is the degrees of freedom. And that will give us a p-value of 0.0011, which makes sense that we're going to be closer to 0.001 because 18.28 is much closer to 18.47 than 16.42. Are there any questions about this step in the process? So next we're asked to interpret the p-value from the calculator in context. Notice that the next question is what conclusion you would draw. So interpreting the p-value is not the same as writing a conclusion. They're asking for different things. interpreting the p-value in context is telling me, what does it mean? What does the p-value represent? The conclusion is using that p-value to either reject or fail to reject the null hypothesis. What do we have evidence for? So for this first part here, interpret the p-value from the calculator in context. Assuming that there is no difference in the true distributions of entrees ordered in this restaurant when no music, French Quarter music, or Italian string music is played. So assuming the null hypothesis is true, there is a 0.0011 probability observing a difference in the distributions of entrees ordered among the 3 treatment groups as large or larger than the ones in this study. Then we can write our conclusion, which is because the p-value 0.0011 is less than our default alpha of 0.05 significance level, we reject the null hypothesis. We have convincing evidence of a difference in the distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played. And again, if you can recall way back when we talked about what things we're allowed to make inference about, we need to have random assignment in order to make an inference about a treatment having an effect on something. Is there any questions about the difference between interpreting a p-value and writing a conclusion based on a p-value? So in a nutshell, this is how we do a chi-square test for homogeneity once we've checked conditions. All right, so suppose the conditions are met. You can use the chi-square test for homogeneity to test the null hypothesis that there is no difference in the distribution of a categorical variable for several populations or treatments versus the alternative that there is a difference in the distribution of a categorical variable for several populations or treatments. We will start by finding the expected count for each category, assuming that the null hypothesis is true. And then calculate the chi-square statistic as we have previously, where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, chi-square statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. Okay. So that's the chi-square test for homogeneity in a nutshell. That's what we have to do. So we need a moment to write anything down from this screen. Please raise your hand. So we have a follow-up analysis for the example we just saw. The chi-square test for homogeneity allows us to compare the distribution of a categorical variable for any number of populations or treatments. If the test allows us to reject the null hypothesis of no difference, we then want to do a follow-up analysis that examines the differences in detail. So once again, we can only do a follow-up analysis if we reject the null hypothesis, meaning we found significant results and we have evidence for the alternative. We'll start by examining which cells in the two-way table show large deviations between the observed and expected counts. Then look at the individual components to see which terms contribute most to the chi-square statistic. We have this little table here that has a breakdown of the 3 treatments and essentially, the French, Italian, and other categories here. And it starts with the observed count, expected count under that, and then the contribution to the chi-square statistic under that. It has it all kind of in one shot here. Looking at the output, we see that just 2 of the 9 components that make up the chi-square statistic contribute about 14, almost 77% of the total chi-square, equaling 18.28. We are led to a specific conclusion. Orders of Italian entrees are strongly affected by Italian and French music. So we can kind of narrow down our conclusion a little bit doing a follow-up analysis. Is there any questions about our follow-up analysis? Anything I can clarify? So now we're moving on to the next type of test, right? Checking for association. Another common situation that leads to a two-way table is when a single random sample of individuals is chosen from a single population and then classified based on two categorical variables. In that case, our goal is to analyze the relationship between the variables. Our null hypothesis is that there is no association between the two categorical variables in the population of interest. The alternative hypothesis is that there is an association between the variables. So in this type of a test, the test for independence, we're checking for an association. Does one variable have an effect on the other variable? The 10% and large counts conditions for the chi-square test for independence are the same as the homogeneity test. There's a slight difference in the random condition for the two tests. A test for independence uses data from one sample, but a test for homogeneity uses data from two or more samples or groups. Right. So we have our conditions here. Random, the data come from a well-designed random sample or a randomized experiment. 10% and large counts are the same as we've seen. Does anyone want a moment to write anything down from this screen? Please raise your hand. And this is the basic rundown on how to do the chi-square test for independence. So suppose the conditions are met. You can use the chi-square test for independence to test the null hypothesis. There is no association between two categorical variables in the population of interest versus the alternative. There is an association between two categorical variables in the population of interest. We must start by finding the expected count for each category, assuming the null hypothesis is true. Then calculate the chi-square statistic, same as we have, where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, the chi-squared statistic has approximately a chi-square distribution with degrees of freedom equaling number of rows -1 times number of columns -1. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. And this is what I was saying, it's not showing all the process and calculation for this because it's the same set of calculations we did for the previous example. It's just going to use data from a new example. All right, but the calculations, how to find the expected count, how to calculate the chi-square statistic works exactly the same when doing this type of test for independence. So we'll look at this example. And this has to do with choosing the right type of chi-square test. So we've seen that there's two different types. You need to be able to choose properly. Are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down the results by gender. So we have the male and female students and then whether or not they have fright symptoms. They used some fancy software called Minitab, which we do not have access to do a chi-square test using the data shown below. Right. And again, this has our observed count, expected count, and contribution to the chi-square statistic for each of the 4 entries in that table. All right, so male and female, and whether or not they have lingering fear. This also is showing our chi-square statistic, degrees of freedom, and p-value. So we have all the information we need already. So explain why a chi-square test for independence and not a chi-square test for homogeneity should be used in this setting. Here's the reasoning. The data were produced using a single random sample of college students who were then classified by gender and whether or not they had lingering fright symptoms. Chi-square test for homogeneity requires independent random samples from each population. So had they collected independent samples from the population of male students and the population of female students separately, and had them answer the question and done the thing with the lingering fear and all that stuff, then we could use a chi-square test for homogeneity, because we would have independent random samples from 2 separate groups or populations. But because we took a single random sample from a larger population and then classified them by gender, this becomes a test for independence. Is there anything I can clarify about that? So I want to state an appropriate pair of hypotheses for researchers to test this setting. We have the null hypothesis that there is no association between gender and ongoing fright symptoms in the population of college students. The alternative hypothesis is that there is an association between gender and ongoing fright symptoms in the population of college students. And again, the hypotheses are almost identical, with the only difference being there is no association versus there is an association. Other than that, they are copying and pasting the same thing. All right, and so first they're checking to see which cell contributes most to the chi-square statistic. In what way does this cell differ from what the null hypothesis suggests? Well, men who admit to having lingering fright symptoms account for the largest component of the chi-square statistic, 1.883 of the total 4.028. All right. And so, I mean, if we look at this one here, 1.833 is almost twice the closest ones here. It's more than twice. All right. Far fewer men in the sample admitted to fright symptoms, 7, than we would expect if the null hypothesis were true, 11.69. So then the next part is asking to interpret the p-value in context, then write a conclusion based on the significance level of 0.01. So again, we have 2 separate parts to write for this, the interpretation and then the conclusion. If gender and ongoing fright symptoms really are independent in the population of interest, there is a 0.045 chance of obtaining a random sample of 117 students that gives a chi-square statistic of 4.028 or higher. That's the interpretation. Because the p-value 0.045 is greater than 0.01, we would fail to reject the null hypothesis. We do not have convincing evidence that there is an association between gender and fright symptoms in the population of college students. So again, we have those 2 parts. We interpreted the p-value, and then we wrote the conclusion based on that p-value and the significance level we were given. Is there any questions? Is there anything I can clarify from this example? All right, so that was the rundown on how to do inference for 2-way tables. So we kind of saw all of these check marks today. We need to compare conditional distributions, state appropriate hypotheses, and compute expected counts, calculate chi-square statistic, degrees of freedom, and p-value, perform chi-square test for homogeneity, and perform a chi-square test for independence. And we need to be able to choose the appropriate chi-square test. Right? And again, the calculations are the same for both of these tests. I even saw something about like the AP exam that if you're not entirely sure which test you're supposed to use, and you're supposed to state which inference method you're using, it's better to say that you're going to perform a chi-square test and leave it at that than to choose the wrong one. I'm not sure why that's the case, but that's what I've been told. So if you're not sure, just don't tell them which one you're doing. All right. That is the end of that presentation. All right, so I know that was probably a lot of information and it was really dry and I was droning on, so I apologize for that. Tomorrow we'll be doing practice with this stuff. All right, we'll be doing another Desmos activity because I do find that those are a little easier to do math with, and I can now have them check your stuff as you do it, which gives you some nice instant feedback and you can see if you're making mistakes or if you're doing things properly, which is always helpful. So that'll happen tomorrow. We'll also see a short video tomorrow. It's like 2.5 minutes long, 3 minutes maybe, showing how to use the calculators to do these things with your chi-square statistic. So there'll be that tomorrow as well. Lastly, and again, I'm going to beat the drum here a little bit. For those of you who are registered to take the AP exam, there's a chunk of you who still have not either downloaded the app and logged in, or you haven't checked to see if the app is on your computer and logged in to the testing app. This needs to happen, right? If you have an older computer from school, right? I've noticed with the silver Samsung Chromebooks that are pretty old, if you have one of those, chances are it will not run the app. Right? You need to know that now rather than a couple days before your first AP exam. That would be horrible. You do not have enough time. You might not have enough time to get another device at that point. All right, so please confirm that your device can download the app and that you can log in. Logging in confirms that the download worked. All right, so that needs to be done. Like now, today, check to make sure these things work. Because if they don't, you need to make arrangements to get a different device. All right, if you're not sure whether or not you've logged in and the thing works, you can ask me. I'll check my little records and see if you have logged into the app and if it's working. All right. If you have any other questions, comments, or concerns, please let me know. Ask me now, send me a message, send me an email, something. Get the help you need. But other than that, that is all that we have for today. Have a great rest of your day, and I will see you all tomorrow.